Greetings, everyone. We're very excited to be here with you today at Hack in Paris. This is holding the stick at both ends, fuzzing the RDP client and server. And before we start, let me just have a quick word about ourselves. My name is Reiner, and I'm a security researcher at CyberArk Labs. And with me today, I have Porath, who is also a security researcher in my group. And we are here to tell you about our journey of fuzzing RDP. Our agenda for this presentation will be as follows. First, we're going to talk about our motivation, and we will provide some of the basics of RDP that will be necessary for our fuzzing efforts. Then we'll jump right to the deep water and start to build our fuzzing environment from the ground up. We'll explain what made this fuzzing target unique and how we were able to finally fuzz that. After that, we will talk about the results of our journey, and of course, we will dissect one of the issues that we were able to find in RDP. And finally, we'll have a mandatory summary session, and we will discuss some future work opportunities in that area. So without any further ado, let's start right in with RDP. All right, so this is what the end user usually knows as RDP, or the remote desktop protocol. We probably all know this flow. You need to access a remote Windows machine, so you fire up mstsc.exe and you get right to it. But as we are soon to find out, there is plenty that is going on behind the scenes of RDP in order to make this remote connection possible. But before we can get into that, let's talk about the motivation for this project. So using a simple showdown query, we see that there are more than 5 million RDP servers exposed to the internet alone. And as you may imagine, there are probably plenty more behind firewalls and inside internal network. And it is clear that RDP is widely used by Windows users. So how can this serve an attacker? Mainly, there are two attack vectors. The first one is the more traditional quote-unquote vector, in which the attacker is trying to get access into an internal network. There is an RDP server in this network that is exposed to the internet, but the attacker doesn't have any credentials for it for obvious reasons. The attacker can then exploit a vulnerability, potentially a vulnerability in the RDP server, and use it to gain unauthorized access to the server, and from there to the entire network. So going to the other vector, the second one, it is not as common and it targets the RDP client. Here we have an attacker who was already able to gain access into some server or a virtual machine, and they can wait for an administrator to connect to the server and then exploit a vulnerability in the RDP client, which will allow them to gain their privileges, the administrator's privileges, and effectively execute code on their machine. Now, these two attack vectors are not merely theoretical. There have been some real-life examples for both of them in the last few years. And just to name a couple, we saw Deja Blue. For the first attack vector, it was an integer overflow bug in a decompress function in the RDP server that allowed attackers to run arbitrary code remotely. And for the second attack vector, we saw reverse RDP, which was a past traversal bug in Microsoft's RDP client that allowed the RDP server to run arbitrary applications on a connecting client. So we can agree that RDP can be a lucrative target for attackers, but why should we fuzz it? To answer that, let's have a quick look at the RDP attack surface. So as you can see from this simple query here, we have more than 190 RDP-related binaries and drivers and executables and so on. And this is on a vanilla Windows installation. So it's quite a lot of code, we can agree. And manual review doesn't seem like a great option at this point. And this is why we decided eventually to go with fuzzing. Before we can start the fuzzing, let's understand the basics of RDP. So on to reading the docs. After downloading the relevant files from MSDN, we had around 30 specification documents with hundreds of pages in each and every one of them. And of course, sadly, there wasn't any pictures in them. RDP is a complex protocol. It relies on several layers of different protocols and standards to be able to function. It usually runs over TCP, as you can see here, although UDP can also be an option for it. And RDP also uses TPKT, X.224, and T.125 MCS for data encapsulation. An RDP connection has some general features to it that we thought we should mention here. The first one is negotiation. Many of the connection's functionalities can be negotiated between the client and the server. I'm talking about things like the security level of the connection, the encryption and compression algorithms being used, supported formats, etc. The second thing is data compression. So in some of the layers of RDP, the data being sent is compressed by the sender and then decompressed by the receiver. And you know that compression code can be erroneous many times. So having a lot of compression in the target code is a great thing. And this is, of course, me talking from the attacker's standpoint. And the last one here is RDP security. So the protocol has some security features built into it. It mandates some sort of data encryption level in every connection, which makes the protocol somewhat secure at the base level. So this was the general info we wanted to share. Now let's have a look at a bit of more details. So RDP, we refer to it as a protocol of protocols. And this was coined by, I think, Malware Tech. And since I heard it, I've been using it because it really describes RDP well, in my opinion. So an RDP connection is comprised of multiple different channels, as you can see here. And going from the top down, we start with static channels. These channels are being opened in every single connection. Then we have virtual static channels, which are an extension to the static channels, and they are optional, meaning they are negotiated in the connection initialization phase between the client and the server. And finally, we have the dynamic virtual channels that can be created and destroyed throughout the connection lifetime upon request. And those are encapsulated inside one other static virtual channel. Now, each of those channels serves a completely different purpose. So you can have, for example, a user input channel, a display monitor channel, an audio channel, and so on and so forth. And every channel has its own initialization sequence, message types, and data structures, which basically makes it its own protocol, hence calling RDP the protocol of protocols. Now, here we can see a quick overview of the actual software components at play in an RDP connection. So first, on the right side, we have the client. There we have mstse.exe and also the DLL mstse.ax, which contains most of the protocol logic on the client side. Of course, as you might imagine, this makes it a huge binary with almost 19,000 functions. At least we are lucky enough to have public symbols for it, so we take what we get. As you may imagine, there's a lot of ground to cover on that side, and this is one of the reasons we wanted, again, to go with fuzzing. Now, onto the other side of the server, here we have the main server service, which is hosted inside an SVC host. And this one loads a few DLLs to handle the protocol's logic. Other than that, the server also runs a few other processes for handling different channels, the clipboard channel, for example. And finally, the server also has a few kernel drivers for some channels functionality. Take, for example, the device redirection channel you can see here. So now that we have the basic understanding of RDP, let's talk about fuzzing.
Okay, so now that we understand RDP and the potential damage in a vulnerability in it, let's talk about how to fuzz it. But before we can do that, let's talk about fuzzing in general. So this is a classic setup of what fuzzing looks like. On the right-hand side, we have our target process, and on the left, we have the fuzzer that generates test cases and inputs them into the target. Additionally, we have the code coverage engine that tracks the execution flow of the target and reports it back to the fuzzer. So in this example, the target is a PDF reader, and the fuzzer generates PDF files and opens them with the reader. Pretty straightforward. Now the question is, how can we adapt that to the RDP case? Clearly there are some differences. First of all, we need two machines. We need a server and a client. And secondly, we don't have a very clear choice of what the input files will be. So what can we do? So the first thing we had to figure out when trying to fuzz RDP was how can we send inputs to our target, be it the server or the client. And going into this project, we had four options. The first was to take an open source solution and modify it so that it will send our fuzzing messages as well. The second one was to write everything from scratch, write our own custom RDP client or server and use it to send our messages. The third one was to use snapshot-based fuzzing and basically send inputs simply by writing to a specific memory, to a specific location in memory. Finally, we had the option of what we call living off the land, basically tapping into some existing solution and using exported APIs or code injection to send our messages. And eventually what we chose to go for is, for the client case, we used an existing solution. And the reason for that is that the server side of Microsoft's RDP allows very convenient APIs to send messages to the client. And for the server side, for fuzzing the server side, we used an open source solution, namely we modified FreeRDP. So the basic setup for fuzzing RDP looks something like this. And I should say that the credit for these architectures should go to Park, Young, Kim, and Lee from Korea University, and you should really check out their Black Hat talk that we linked here. In any case, what we have is, again, on the right-hand side, we have our target, in this case, the RDP client, and as before, the fuzzer and the code coverage engine. The difference is that the inputs that the fuzzer generates are not directly fed into the target, but first they go to the server side, and an agent that we wrote reads them and sends them over the connection as if they came from the RDP server. So this looks something like this. And let me just mention that the same setup is used for the server-side fuzzing. Essentially, we just need to mirror everything. Now, for the client side, we optimized it quite a bit, so it looked something like this by the end. So again, on the right-hand side, we have MSTSC, which is the Windows RDP client, and we have AFL Fuzz as our fuzzer, and the code coverage engine is based on DynamoRio and WinAFL. Now, the difference is that we used MSTSC, instead of connecting to a remote server, we used it to connect to localhost. So it's connecting to the same machine. And then AFL Fuzz can simply send the messages to our fuzz agent on the same machine, and it will direct those messages to the target as if it came from the server side of the RDP. And the upshot of that is that we can run concurrently many instances of this fuzzer and target on the same machine. Okay, so now we can send messages. We need to decide what we're sending. And as we said, practically every channel is its own protocol. So we chose to fuzz on a channel by channel basis, meaning every time we would pick one channel and we would only fuzz messages on that channel. And for the most part, that is sufficient because the channels are independent, so we can cover most of their logic simply by fuzzing them and ignoring everything else. Now there's a bit of a side note, but when we wanted to fuzz the server side, then we needed to fuzz the RDP server runs on a Windows service that is automatically executed when the machine boots. So we have no control over the creation of the process. And therefore, we cannot control it with DynamoRio. So what we had to do is we had to add the ability to attach to a running process with DynamoRio which was not supported out of the box. And if you find this useful, then we're happy to say that we've merged this functionality to the main branch of DynamoRio, so everyone can use it now. Okay, so now we can connect and we know what we are sending. And the next thing we had to overcome was the following issue. We are tapping into a live connection. So there's a lot of data that goes from one side to the other that has nothing to do with the fuzzing process. Basically just RDP doing RDP things. And we somehow need to differentiate the normal RDP messages from our fuzzing messages. So it looks something like this. We have several normal messages that are transferred on this channel. And the last one is our fuzzing message, essentially a test case that the fuzzer generated. But in order for coverage-guided fuzzing to work, we must maintain a one-to-one correspondence between the inputs the fuzzer generated and the code paths that they triggered. And to achieve that, we developed this background fuzzing, essentially differentiating our messages from the regular messages. And the way we did it is by adding a marker. So in this case, the marker is the first byte of the message. As you can see on the normal messages, it is hexa20. And on our messages, on the fuzzing messages, it's hexaFF. And that allows the code coverage engine to differentiate the fuzzing messages from normal messages. So let's look at an example. So this example is taken from the RDP sound channel, which is used to redirect sounds from the RDP server to the RDP client. And according to the docs, the first byte of every message is the type of the messages we are sending. And the supported values for the message type is from 1 to hexad. So what we can do in this case is use the most significant bit of this first byte as our marker. So our agent will turn this bit on before sending any fuzzing messages. And WinAFL will check if this bit is on before the message is handled. If the bit is on, then we know that this is a fuzzing message. We know that we need to track code coverage for it. And finally, we turn the bit off so that the execution will continue as it should, as it normally does. If the bit is off to begin with, then we know that this message has nothing to do with the fuzzing process, and we can simply ignore it, then don't track any coverage for it. Great, so now we have a running fuzzer. We can start sending messages, but we came across a different problem, essentially the statefulness of the connection. Basically, what we found is that for some channels, if 2 consecutive messages are invalid, then the client will simply close the connection and terminate. And obviously, we cannot have that for the fuzzing. We cannot continue fuzzing once everything is closed. So we had 2 solutions to overcome this. One was using code patches, basically just stopping the target from actually exiting. And the other was using grammar enforcement, basically limiting what the fuzzer can send so it never reaches those bad paths. So let me explain code patches. So this is an example, again, from the graphics channel. And here we can see that if some error is detected, there are 2 options. Either we exit, or we log an error and we reconnect. And what we did, we basically patched so that we always go through the reconnection path and never through the exiting path. And the cool way to do it is using DynamoRio functionality that's called DynamoRio rep. Basically what it does is we have this original pointer where we don't want to ever go, and we have this replacement pointer. So, and we just tell the program, whenever you get to the bad path, just go to the good path. So in our case, the original would be the exiting code path, and the replacement would be the reconnect code. Additionally, as I said, we've used grammar enforcement. So basically, we enforce some size limitation of the messages, some of the values, the divisibility of the size, and so forth. And one question was, how can we find what the grammar should look like? So the first thing we did is read the documentation. Microsoft has great and vast documentation on RDP, and we got most of the grammar from it. And when that didn't work, we had to go through either reverse engineering the code to see what is bad, what is regarded as bad grammar. And when that failed, we had to trace the failed execution and find out what went wrong and how we can avoid that. Now, an important remark about grammar is that whenever we narrow what the fuzzer can do, we might miss some interesting path. So what we chose to do is to enforce as little as we could, but still enough to ensure that the connection is never closed. Okay, so this is great. Now we have a running fuzzer, and it says messages. Each test case is one message. And we started running. And after a while, we found that the coverage was pretty low. And what we realized is that most of the logic of an RDP channel actually depends on a sequence of messages and not a single one. So what we decided to do is to create larger test cases that are actually comprised of several messages and not a single one. So for example, the first test case might be 3 messages, the second 2 messages, and so on. So let's give an example of why this is necessary. So this is again from the graphics channel. What we have here is a map surface to output PDU, PDU being protocol data unit, so the basic message of the protocol. And what it does is it maps a predefined surface to an output buffer. But as you can see, it accepts a surface ID that has to have been created previously using a create surface PDU. So the map surface to output PDU makes no sense unless there was a create surface PDU preceding it. That's why we had to use this multi-input solution. So the way we implemented it is using a feature of WinAFL called AFL Dictionary. Basically, AFL Dictionary just tells the fuzzer, here's a sequence of bytes, and you should try using it from time to time in your input mutations. And we used it in a following manner. We used it to separate the protocol messages. So these underscore, 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 command, XX would be the dictionary entry. And the agent would use that to split the test case into multiple messages. Now, an important remark is that the fuzzer will only complete the fuzzing iteration and create the next test case once the last message in the sequence is sent. So the way we did that is by adding a second marker. Basically, not just saying this is a fuzzing message, but this is a fuzzing message that is also the last in a sequence of messages. Now, that was great, and for most of the channels, that was sufficient. However, we did come across cases in which we needed to actually run on multiple channels. For example, this is from the video channel, and as you can see, some of the data is sent on the control channel and some on a data channel, on 2 different virtual channels. So we had to somehow create messages that are sent on 2 different channels. And we did it in a very similar fashion. Basically, the type of the message would also tell the agent on which channel to send the next message. So for example, message of type 7 would go on the control channel, message of type 2 would go on the data channel, and message of type 3 would go, say, on the control channel again. Okay, so now we have something that runs and sends messages, But one of the problems we had was actually locating our target function. So we can send messages, but we need to know who deals with the messages on the target. And this is not such an easy problem because RDP has a huge code base and it's hard to locate the correct function. So what we ended up doing is downloading all the relevant PDBs and extracting the function names from each of them. And we created a small database that connected a function name to the binary that it lives in. Now we had some luck because most of our target functions had the form C class name on data received. So we would say C audio channel on data received, and that helped speed things up. As a side note, I would say that it would be very beneficial for the security community to have a complete database of all available type info and function names of all the public Microsoft PDBs. And we didn't get around to it, but it would be great if someone would take the glove and do it. A few fuzzing iterations later, we found our first crash. Hurrah! However, we started analyzing it and we tried to reproduce it, just send the same messages, and it did not reproduce. Basically, what we realized is that this is a problem of the statefulness of the protocol. Basically, some previous message put the target in a condition that when the subsequent message arrived, it crashed. But it would not reproduce by simply running the last message. So we had to come up with a solution that would allow us to analyze crashes that are not reproducible. And this is what we came up with. It's a bit much, but don't worry. So basically, we had this watchdog, and it would wait until a crash was detected. And whenever a crash was detected, it would generate a dump file. Now, we would analyze this dump file with a windbag script, and we would extract the call stack that caused the crash. Now, we would compare this call stack to the previous call stacks that we found, and if it's an old one, then we can simply discard it. It's old news. But if it's a new one, then it would send us an email saying, hey, you found a crash, good job, go check it out. And that looks something like this. And now that we understand how we did it, I will let Jaquette explain what we found.
All right, so let's talk about the results. So this is an example of one of the channels that we fuzz, and these are the stats for it. And you can see that the execution speed is not so fast, to say the least. However, the fuzz did manage to find some crashes, which is what's actually important here. So in a more high-level view, we were fuzzing for about 1 month of, this is actually fuzzers running. We fuzzed 15 channels in both directions, the client and the server, and we found 5 bugs. So let's now go ahead and dive into one of those bugs. So this one was found in the audio playback channel. And what is this channel? Basically, it is used to play sounds on the client that were generated on the server. So basically, it allows the client to hear what's going on the server's machine. So this is how it all started. This was the dump file that was created by the crashing input. And this is the input that was responsible for the crash. So here, if we take a look at this for a minute, this is a good example for why the multi-input fuzzing or mentioned that we implemented was very helpful in this process. So as you can see here, the input has 4 different PDUs or 4 different RDP packets. All right, so naturally, we go to the crashing code. And if we clean up the pseudocode a little bit of the crashing function, we get something like this. As you can see, the crash happens in the last line, where we have an access to an element of a formats array. So let's try to understand what this array is all about. Before we can understand the bug, we need to take a closer look at what a legitimate flow in this channel looks like. So First, the server sends a list of the sound formats it supports to the client. When getting the formats list, the client will allocate an array containing all the details about those formats for a later use when decoding sound data messages from the server. Then the server is practically free to send sound data in any of the formats that were announced before. And then the client uses the format index to process the data. Here in this example, you can see 3 formats being announced, and then 1 data packet that is using the third format. So no issues here. Now, based on that, let's take a look at what the crashing input caused the message flow to look like and see what happened before the crash. So it starts like the legitimate flow. The server sends a list of 3 formats that it supports. The client then allocates the array of those 3 formats. Then the server sends data in format 3, and the client can process it normally with no issues. Now, this is where it gets interesting. The next thing that happens is that the server updates the list of supported formats with a list that now only contains 1 format, basically causing the client to free the format array it has and to allocate a new one, this time with only 1 format in it. Next, the server sends a sound data message with format 3, even though the client only has 1 format to work with. So as you can imagine, the client tries to access the third format, causing an out-of-bound read and causing the client to crash. If we take another look at the function again, in the client, we see that the client does account for changes in the format we can see that the client account for changes in the format when the format is in the current message is different from the format in the last message. However, here, this wasn't the case in our crash. What the fuzzer did here is not to change the format itself, because it's still 3, it's still the same index, but the fuzzer changed the whole format array for a smaller one, so from 3 to 1 size of array, which ultimately led to an out-of-bound access and to crashing the target. So as you can see, this is an out-of-bound read with a very limited impact, but it was a good example and it demonstrates how effective the multi-input fuzzing approach was. All right, so we had quite a lot of fun, I think. So let's summarize the session. The first point we'd like to make is that we believe, at least, that nothing can be deemed unfuzzable. This project shows that no matter how complex the target might be, you can always find a way to fuzz that, especially with newer snapshot-based fuzzers, like, for example, what the fuzz by overclock. And also, just let the fuzzer do the work for you. You don't really want to put all that effort and manually analyze your targets, right? Because what's the fun in that? All right, regarding future work in the field, we do believe that it's still worth putting more effort into fuzzing RDP. Our project was not ideal in many ways, and it can be improved on in different aspects. Due to the huge code base and the number of logical channels, we bet that there are still more stuff to find in RDP, and we may go back to pursuing it in the near future. The other thing is that the platform we've built around fuzzing RDP can be directed at a completely different target on Windows. So by platform, we mean the multi-input fuzzing, the attaching to Windows services, automatically analyzing crashes, and all that other stuff. And we started doing just that for some components in the Windows Hyper-V, and also for a few RPC servers on Windows. And we got some promising preliminary results. So do expect to hear more about that in the near future. We also pushed all of our tools to GitHub, all the stuff that we used and developed in the project. You can check them out in the URL down here. You will find all the stuff we talked about today over this on this repo. It's not an off-the-shelf, ready-to-use type of thing, but it can give you a jump start if you're looking to fuzz something similar on Windows. And also, the main features we added to WinAFL and to Dynamo Rio are now merged into the main branch of the tools, and they are available for anyone to use.
Finally, let me just say that we encourage everyone to use the techniques and tools that we've developed in any way they see fit, and we're happy to discuss everything fuzzing related, so please reach out to us. The best place to find us is on Twitter. And thank you very much. I hope you enjoyed this session. I hope you will enjoy your conference, and thank you for the organizers for having us. Good day.